Afternoon viewers, all the students are welcome to this BISEC series of presentation in microbiology. Today's topic for discussion and presentation is all about enzymes, especially the general characteristics, types of nomenclature systems and modes of its classification. With me I have Sri Rikin Bhai Parikh to take part in the discussion. The first thing I would like to tell about enzyme is that the term was coined as late as in 1800 to describe the effervescences observed within the fermented broth by the yeast. The molecules called enzymes were first crystallized by J.B. Sumner in 1926 in terms of urease, and it was demonstrated by him that enzymes are in fact protein. Now, these class of compounds are highly efficient and extraordinarily powerful molecules which are acting like catalysts, and because they are catalysts of the biological nature, they share most of the chemical properties of the typical chemical catalyst. That is to say, they are not consumed during the reaction, they just speed up the reaction rate, etc. The enzymes are in fact occurring in the diverse kind of varieties within every living cell. In fact, a very simplest kind of single cell may contain hundreds of different types of enzymes, and each one of them in numerous copy numbers. Together, this array of enzymes are capable to catalyze number of biochemical reactions which constitute the entire physiology of the organisms. And in fact, it is these metabolic differences and enzymatic reactions which makes the basis for differentiation within the different forms of life. This class of molecules are possessing lot of unique properties which makes them most wonderful molecules, or they can be regarded as the miracle molecules. The enzymatic reactions which are taking place are of a nature that are just not possible under ordinary circumstances, that is at the physiological conditions, unless the reactions are aided up by the enzymes. And these enzymes are in fact able to speed up the reaction to great magnitude, that is up to 10⁻³ to 10⁻20 times fast than the reaction catalyzed in a non-enzymatic way. Now, important thing about enzymatic reaction is that they proceed towards the attainment of equilibrium status in a very rapid manner, but interestingly, the point of equilibrium is not altered, that is, position of the equilibrium remains the same whether the reaction is enzyme catalyzed or not. Now, another important thing is that the activation energy required by the molecule to undergo reaction is lowered down, and for this reason the chemical reaction or enzymatic reaction can take place at a much lower energy levels without requiring additional energy in the form of heat or in any other forms. These reactions are in fact substrate specific. Each enzyme is very much choosy in selecting its substrate and is able to act upon only and only upon the specific substrate. Now, of course, there are exceptions wherein some enzymes are able to act upon group of compounds, class of compound, but still, despite that, the specificity is maintained. The enzymes are also specific in terms of stereo forms. Enzyme can distinguish between the optical isomers and stereoisomers of different types. The reaction which is taking place in the presence of enzyme are free from different type of byproducts. So in a way, it is like running over the express highway where there are no additional exit or entry points, unless there are few specified ones. So when reaction is catalyzed by enzyme, the chances for formation of unwanted byproducts are minimized, and the entire set of substrate or maximum part of it is channelized towards the final products only. So that is the beauty of enzyme reactions. Now, the enzymes are energy efficient in a way that they are able to couple different type of reactions. Some reactions which are endothermic, others which are exothermic, can be coupled together by an enzyme, and the energy released during one reaction is captured and is utilized in the energy requiring reaction which is going on concomitantly. Now, these class of compounds have also evolved with a mechanism for regulation, and these allosteric regulation makes the basis for control of entire metabolic repertoire. So these allosteric activity allosteric mechanism of an enzyme regulation is because of the specific structure of the enzyme, which allows the binding of substrate as well as effector molecules to its site. Now, how these enzymes are named and classified is an important area. If a large number of enzymes are known and the list is being appended every day, every scientist have been using the name in their own way. So this is going to lead to a kind of chaos where there will be a lot of ambiguity in knowing the enzymes. So until the number of enzymes which were known to us was limited, uncontrolled naming patterns were acceptable and would not be having much influence over the scientific research. But when the number of enzymes are growing rapidly and the names which have been in use are often misleading, and often they do not convey the precise meaning of what kind of chemical reaction is catalyzed by the enzyme. This can be exemplified by the enzymes, enzymatic names like diaphorase or catalase, wherein it is not clarified that what kind of chemical reaction the enzyme is catalyzing here. Similarly, there are different groups of reactions which are in fact catalyzing the similar reaction, and therefore different names may not be needed. So this kind of examples would lead to a kind of ambiguity in knowing the enzyme, in naming the enzymes. Also, some of the established names, that is the enzymatic names which were used currently, were reconceptualized. A good example is that of synthetase. This name is used only in a distinctive cases where ATP is required and is consumed during the reaction. Whereas in the earlier literature, often synthase and synthetase type of names were used interchangeably. And with this sort of understanding, the compilation of enzymatic names in a scientific way is going on, and the entries which were initially just 712 in the year of 1961, that is initially, is presently having 3,196 entries, as has been updated in the year 1992. Now, ways of naming the enzymes and the responsibility to do so was in fact assigned to a body of experts, and this body is known as International Union of Biochemists and Molecular Biologists. So the work carried out by this committee with regards to nomenclature and classification of enzyme became a landmark for most of the enzymologists and biochemists worldwide, and it is considered to be the most authentic record of enzyme nomenclature. Now, I would request Professor Rikinbhai Parikh to give idea about nomenclature patterns used in enzyme. I would request him to start with the introduction about the IUPAC body, which has worked out the scheme for classifying and naming the enzymes. Rikinbhai, please.
Thank you, sir. And once again, good afternoon to all of you. As sir has discussed and given you the brief idea regarding what the enzymes are and general properties and some basic aspects of enzymes that sir has discussed. Now, after understanding that concepts of enzymes, the structural properties, the physicochemical natures of enzyme, now we will move further in the aspect of nomenclature and classification of the enzyme. As Yagnik sir has given this brief idea about the international union which has taken this responsibility for giving the perfect exact classification and nomenclature of enzyme. Initially it was assigned to the IUPAC, that is the body, the name of the body is the International Union for Pure and Applied Chemistry. Then Third International Congress of Biochemistry, in 1955 August, it was initially started. Then set of International Commission on Enzyme was been started, formerly the International Union of Biochemistry, that is also known as IUB. That body has started the nomenclature and classification of enzymes to consider the classification and nomenclature of the enzyme and coenzyme, their units of activity and standard methods of assay, together with the symbols used in the description of enzyme kinetics. So this type of the basic aspects they have covered, that how to give name to any unknown type of the enzyme which has been invented by any scientist throughout the world. And as sir has discussed, priorly so many confusions occurs by the name of scientists, the people who had invented that type of the enzymes, and that was the biggest problem. But now with the help of this International Union of Biochemistry, they have suggested this type of the working ideas and principles. They have given two types of the naming procedure. First one is a common name, that is a trivial name, and a systematic name. Systematic name is somewhat what we are interested in, that how this systematic name come arise and which type of the methods and principles are used for giving the systematic name to any trivial type of the enzyme. In this trivial naming, these are the basic principles or aspects which should kept in our mind before giving any trivial name to any type of the enzyme. General, working and current in use, that should be general, working and current for the use. That type of the name should be suggested by the person who has submitted. The person who has submitted will give the name to that type of the enzyme. Common names, that suffix ase should be placed after the substrate. That was the very primitive type of the idea to give name to any type of the enzyme, that they have to consider that the particular enzyme is acted upon by which type of the substrate. The example what we take, we can take the example of urease enzyme. When we say urease, then it is clear in our mind that substrate should be urea, and we have put the suffix ase after urea, so it becomes urease. Then historic type of the enzymes are also there. The names are there, trypsin, amylase. So that type of the enzyme are not following this, but it is a historically proven and accepted type of the names. After the gene, that is RAK, ATPase, after some characteristic. So these are the different aspects, that after the name of gene we have to put it is enzyme, is suffix, and after the characteristic, that is HSP70, that is a heat shock protein, in case of that also we have to put this type of the ATPase. So this systematic naming goes further, that formed per rules show the enzymes and enzyme as exactly as possible. The name, confusing name should be avoided. Uniquely define the reaction to be catalyzed. In systematic type of the naming, it is very important characteristic that unique, they have to be unique in specific in the reaction what it has been catalyzing, combining the substrate plus reaction type. That was the advancement. that you have to combine not only substrate name, you have to put the suffix ase, but substrate name plus the type of reaction which has been catalyzed, that also you have to add in that. Alcohol dehydrogenase. So as the name indicate, we can understand that it will remove H from the alcohol by the process oxidation. So that all we have put in the name of alcohol dehydrogenase. Alcohol is a substrate and dehydrogenation, that is the removal of H. So that is the reaction being catalyzed. So we have combined both of them, name of the substrate and the reaction being catalyzed. So the name of the enzyme we place, that is alcohol dehydrogenase. The lactate NAD oxidoreductase, it is another example by which you can also understand that what it is doing, that lactate is a substrate, that is a lactic acid, and NAD oxidoreductase means oxidoreductase is you can say oxidation of pyrimidine and NAD, that is reducing to NADH. So this type of the naming pattern was there. Now name ending ase used only for the single enzyme, not to the systems. So now this is another aspect, that when only one enzyme is involved, that is known as single enzyme. In that case, you are just putting down ase suffix after the name of the enzyme, but in case of the system, we cannot do same type of the thing. That is the guideline. Oxidation of succinate by oxygen, the succinate dehydrogenase, cytochrome oxidase in several intermediate carriers called succinate oxidase system. So oxidation of succinate, this is the process which is being catalyzed by more than one type of the enzyme. So it is known as an enzyme system. So we cannot say that succinate deoxidase is the name of the enzyme. Instead, that group of enzymes are involved. So we have to place, we have to say that succinate dehydrogenase system is the correct word for that. So disprove the phenomenon naming when no definite chemical reaction, permease, translocase, replicase, this type of the names can also be used when these phenomenons are not definite. The chemical nature of the enzyme, that is a flavo, heme protein or substrate, that is nucleotides or bases, the simple isotopic exchanges, some catalysis sources, the isoenzymes are one, some group on the basis of type reactions with the name and the substrates. Subsequently, the reactions by one enzyme named on the first enzyme catalyzed step, that as for example, it is acetyl coenzyme A, glyoxylate C acetyl transferase, that is carboxymethyl forming. The written direction of a reaction used for naming, these all type of the characteristics and principles should kept in mind before doing the exact classification and nomenclature. The scheme for classification, that how we have to go for the classification. For that, enzyme commission is required, that is been reported that it has been formed 1961, and they have given numbers, the exact EC numbers, that is enzyme commission number, to each and every type of the enzyme which has been identified and nomenclatured. That once the name is been given, then we have to get the clear idea that it belongs to which class, which subclass, which subclass, and so on. Because many times it happens that the reactions are catalyzed, more or less it is same, but it is just differing in very small way. So confusion, to avoid confusion, this type of the system is been coined by the enzyme commission. The number which is given to them, it is, for example, it is EC 1111. So when we want to understand the name pattern, then we can understand that prefix EC, that contains the 4 elements separated by the points with meaning, that each 1111, these all one are having some meaning, right? The first number shows one of the 6 main divisions. When we go further, move further, we will understand that there are 6 major classes, that it will be discussed by sir later on. So it will be from one of that class. So that first number denotes for that. Second figure indicates the subclass. one fact that is for a class. There are 6 classes for different enzyme groups. Now any one is of one first suffix is for that, then second will be for subclass, that it belongs to which subclass. Third figure gives the subclass, the second part of that subclass, and the fourth figure serial number is subclass. So that way we will move further towards precision. When we start EC, it denotes that is enzyme commission. Then first one will come, that is class, subclass, subclass, and then lastly subclass, that is the latest, the final most reaction which is going on. So in this pattern we have to give the systematic name to each and every type of the enzyme. So from the number also we can understand that which type of the enzyme we are talking about.
So in a way it is more or less like IP address of the computer.
Yeah.
Because there also the naming pattern or naming convention is similar to this, like 192.168.100.1 is a BSNL network IP address for internet protocol. So similar naming system, numbering system was approved for enzyme way back in 1961, and the same under the same naming pattern, each one of the enzyme is classified into one of the 4 categories arranged in a hierarchical manner, and that is how distinctively every enzyme can be assigned to a specific taxonomic group. So this EC number, for example 1.10.3.2, if you feed into the centralized database of enzyme information, then probably you can retrieve this kind of information, starting with EC number at the top, and in the second line you come across accepted name, that is trivial name or general name or name which are commonly used. So this one is a lacase obtained from the sources like fungi and the Japanese lacquer tree like Rus vernicifera, etc. So this is a kind of phenol oxidase enzyme and is more commonly known as lacase. And the reaction catalyzed by this enzyme is 4-benzene plus molecular oxygen, giving 4 molecules of benzosemiquinolone, and water molecule is released. There are other names also by which the enzyme is known. These names are paraphenol, paradiphenol oxidases, or urushiol oxidase. But in addition to these kind of common or trivial name, every enzyme has a specific systemic name, and this systematic name for the enzyme lacase is benzenidiol oxygen oxidoreductase. So you can look into the naming convention applied over here, starting with substrate, and since this is a multi-substrate system, that is a enzyme is able to catalyze the reaction which involve 2 different substrates, because every oxidoreductase are oxidizing one compound and are concomitantly reducing the another one. So both of these substrates are to be mentioned, and these 2 substrates are to be separated by a colon. So that is how a systemic name of the enzyme has been derived, that is benzenidiol double dot, that is hyphen, and oxygen and oxidoreductase. This is the naming system which has been suggested and approved by the Commission. About this enzyme, additional comments are also listed at the end of systemic name, which says that this is a multi-copper enzyme with a low specificity. That means the enzyme can recognize number of different substrates which are of phenolic nature, and it could be ortho or para or type of quinols, and the enzyme knows no distinction among this type of compounds because it has lower substrate specificity. Then the another line gives you information about the direct links to the different type of protein database through which additional information can be derived. So this database like Brenda and XPASI and PDB, that is protein database, etc. You click over it and you directly reach to the protein database of that type, wherein you have additional information about this EC numbered enzyme. And finally, in the information which you retrieve is a list of references which says that who have discovered this enzyme for the first time, or who have analyzed it, studied it to a greater depth, or who have submitted it for the purpose of classification and naming, etc. So this type of bibliographic information is also available within the IUBMB database. Now, as I said, there are several classes of an enzyme. Every enzyme has been placed into one of the 6 classes, and the class is represented usually by the first digit of the EC number. And the first group of enzyme are all oxidoreductase type of enzyme. That means every enzyme having EC number starting with 1, that is number 1 at the first position, are all oxidoreductase type of enzyme. So in this slide I am going to tell you about what oxidoreductase are able to do. These are the enzymes which are able to oxidize one substrate, and this substrate which is oxidized is in fact a hydrogen donor, and the systemic name is, as I said earlier, derived by a structure called donor, double dot, acceptor, and finally oxidoreductase. So this is a naming pattern applicable to all kind of oxidoreductases. A systemic name in case of EC1 type of oxidoreductase is derived in this manner. And also there are common names by which the enzyme is more popularly known. So oxidoreductase are also known by other names like dehydrogenase, and alternatively they are also known as reductase, maybe oxidase, because it is part of their one of the reactions out of the 2 they are catalyzing. But oxidase name is used only when final electron acceptor is the molecular oxygen. Now all kind of oxidoreductase are further classified into different groups, and that comes that is described by second digit. So this second figure in case of all oxidoreductase is describing a group in the hydrogen donor that is undergoing oxidation process. If it is if it is CHOH group which is undergoing the process of oxidation, then the number is always 1. If it is CHO group, and then number is always 2. Likewise, the enzyme commission has given a list depending upon the group which is being oxidized in the hydrogen donor. The second digit of the EC code is generated. In the same way, oxidoreductase are further classified at a third level, wherein the third figure is selected on the basis of type of acceptor. If NADP is the electron acceptor, then the number is 1. If it is cytochrome, it is 2. Number 3 stands for molecular oxygen, serving as the acceptor. So this in fact code number itself tells a lot about the properties of enzyme. For example, it 4 simple digits, 4 simple groups of digit can tell you clearly about the type of reaction it is catalyzed, functional groups which are involved, type of chemical reaction, and the nature of the compounds which are taking part in the reaction. Everything can be understood simply by studying the digits only. Now in the figure which is shown on the left side, you can see that oxidoreductase can be exemplified by a most popular and most commonly known enzyme, very widely studied enzyme, lactate dehydrogenase, which converts lactic acid into pyruvic acid by carrying out its oxidation. The second class of enzymes are all transferases, that is, all enzymes having EC number starting with 2 are all transferase kind of enzymes. As the name suggests, these are the enzymes which are able to in fact carry out transfer of methyl or glycosyl type of groups to the acceptor molecules. And in these type of enzymes, systemic name is derived by a pattern, that is donor to acceptor to group transferase. So write down name of the donor followed by name of the acceptor, and at the end we have to add group transferase. This becomes the systemic name for the enzyme. But common names are generally given by either acceptor or donor followed by group transferase as a suffix. Now, in case of transferases, donor can be coenzyme also, which is responsible for carrying out the transfer of group. And you know, all kind of transamination reactions wherein the amino group and hydrogen are transferred from one compound to the another one are in fact catalyzed by enzyme called transferase, which are commonly known as aminotransferase. A good example is that of amino acid oxidative deamination, which converts L-alanine into pyruvic acid and glutamate. L-alanine and alpha-ketogluteric acid are converted into two molecules of pyruvate and glutamate. So you can see that the amino group is transferred from one compound to the another one. In case of transferases, the second digit indicates the type of group which are transferred. If carbon group is transferred, then the digit is always 1. If aldehydic or ketonic group are transferred, then the enzymes falls within the group of EC number 2.2, etc. And likewise, there are a series of numbers given, each one to distinctively identify a kind of group which is involved in the transfer process by an enzyme. Now, the third set of data, that is third figure, indicates the group transferred. If it is methyl transferases, then 2.1.1. If it is hydroxymethyl or similar type of formyl transferases, then it is number 2 at a third place. Likewise, so this is how enzymes exemplified by alanine transferase belonging to group of EC2 transferase group of compounds, transferase group of enzymes is described. The third category of enzyme are all hydrolases. Now this name is a tricky name because in the past the hydrolases have been used in a distinctive meaning, hydrolytic cleavage of any substrate, especially in terms of CO bond, CN bond, CC bond, or any other type of bond. When it's cleaved in a hydrolytic manner, then the enzyme carrying out this type of catalysis are known as hydrolases. The systematic name always include an ending by the term hydrolases. The common names used for this type of enzyme is always ASE. ASE, that is enzyme ending with name ASE, are mostly hydrolase type of enzymes. This kind of enzymes are able to carry out hydrolytic removal of groups from the substrate, and maybe they are also able to transfer it to the another compound, and in that way they are very much similar to transferase of the group which we have studied previously. But looking at the physiological importance of the enzymatic reaction, where the involvement of water makes the basis for all forms of life, the importance of hydrolysis by the water becomes a very important aspect of enzyme catalyzed reaction, and therefore they are preferentially placed along with hydrolases rather than along with transferases, although they does carry out transfer of compound, transfer of groups. Now, second figure with the hydrolase type of enzyme is to denote that if it is glycosylase or esterase or so on, depending upon that the second number is given, whereas the third digit of hydrolases is derived out of the nature of the substrate. If it is carboxylic acid hydrolases, then it is EC 3.1.1. If it is thiol ester then it is 3.1.2. Phosphoric monoester, then it is 3.1.3. Likewise, the good example of hydrolase type of enzyme is the one which cleaves the pyrophosphate molecule in the presence of water to inorganic phosphate molecules, and the enzyme is known as pyrophosphatase. The fourth class of enzyme are all lyases, which are able to cleave C-C bond, CO bond and carbon-nitrogen bond. But interestingly, they are different from the previous class in a way that they leave behind double bond structure, or maybe they leave behind a ring, or maybe they add a group to a place where the double bond exists. So in a way, one or the other way, double bond is involved in the reaction catalyzed by these enzymes. A systemic name given to this class of enzyme is a substrate group lyase, beginning with the name of substrate, and then that is followed by name of the group, and finally the term lyase. Now hyphen is always needed to separate the term group and lyase, so it is better to say hydro-lyase rather than hydrolase, because otherwise the confusion would arise and this could be avoided. So therefore IUPAC has recommended the dot and the dash must be inserted between group and the term, that is standard ending of lyase. A common name for lyase type of enzyme are very simple. You can say decarboxylase or aldolase or dehydratase, etc. In many instances where reactions are reversible also, then the enzyme could be carrying out lyase activity or maybe a kind of synthetic activity if the reaction is proceeding in the reverse direction. So in that case, synthase is used, but not synthetase, because synthetase is to be used in case of joining two different molecules using the energy by ATP. So that makes the important distinction between two terms of synthase and synthetase. Now the third and last digit, the second digit for lyase type of enzyme could be 1 if it is carbon-carbon lyase, it could be 2 if it is carbon and oxygen lyase, whereas the third number in the EC nomenclature for lyase depend upon the kind of group which is being eliminated. If carbon dioxide is to be removed, then it is 4.1.2, 1.1. If water is removed, then it is 4.2.1, etc. So following the list which is prepared by EC Commission, the second and third digit numbers are accordingly given by the Commission. The another class is of isomerase. Now there are varieties of isomeric forms which are geometric and structural type of isomers, and any sort of structural or geometric changes being brought about by enzyme are in fact known as isomerization, and it comes within the purview of isomerase. Different type of isomeric activities and isomeric enzymes are there. Some of them carrying out isomeric conversion, some are carrying out racemic conversion. They are known as racemases. There are epimerases which converts between epimers. Then there are cis-trans isomers which are able to convert cis to trans or trans to cis type of patterns. There are simple isomerases, tautomerases which are able to carry out tautomeric shift in the molecule. There are mutases and cycloisomerases which carrying out mutarotation of the compound, maybe cyclization of a compound. So in a way, this type of enzymes are not carrying out C change in the molecule, but they are simply converting one of the isomer into another isomeric form. Simply this type of catalytic reactions are known as isomerization, and that could be of pertaining to any kind of geometric or structural changes within the molecule. But the empirical formula doesn't change. That is the main consideration. Now, this conversion could be intramolecular also, and this intramolecular oxidation reduction can also take place, but despite that, it is not classified as oxidoreductase enzyme, because the overall net difference within the whole molecule is not significant to place them, place the conversion into either oxidation or reaction distinctively. The third type of group, third level of classification with isomerase type of enzyme is determined on the basis of substrate which is used by the enzyme. So depending upon substrate, third digit is derived, and you know fourth digit is a distinctive identity of an enzyme which makes the enzyme unique. And the last class of enzyme are all ligases, which are able to join two molecules together, and this joining, coupling of the two molecule, is involving hydrolysis of diphosphate bond in the ATP, or maybe any other forms of energy rich compound. Any type of nucleoside triphosphate derivative could be involved to donate the energy. Now, systemic name in case of ligases is derived from a pattern, that is X colon Y and ligase into bracket ADP forming, because requirement for ADP, that is formation of ADP, is essential part to ligation process. So it has to be shown in bracket wherever the enzyme name is given. You can look into the example which is given below. The enzyme commonly known as glutamine synthetase, as described in the reaction catalyzed by this enzyme is described in the left, wherein you can see that glutamic acid converts into glutamine by an enzyme called glutamine synthetase, and the process requires involvement of ATP and insertion of ammonia molecule. So it is merely an extension of a small chain of glutamic acid into glutamine by adding extra molecules of ammonia. So that way a process is of a ligation, and the common name is glutamine synthetase, but a systemic name could be glutamate-ammonia-ligase, and finally adenyl transferase. So this makes the complete systemic name of the enzyme on the basis of X semicolon Y ligase pattern. So glutamate is one of the substrate, ammonia is another substrates, and ligase is the type of reaction which is catalyzed. Now the term synthetase was used commonly, has now been abandoned in common names. It has been suggested by the Commission that synthetase has been used in past in a disorganized way. That is to say, without distinctively recognize the role of involvement, role of ATP in the enzyme catalyzed process. So the Commission has recommended not to use synthetase at least in the common names. Now, second figure in case of ligases kind of enzyme is in fact could be one where carbon oxygen bonds are involved, could be two if carbon and sulfhydryl bonds are involved, as in acetyl CoA, etc. So depending upon the guideline given in the EC list, the second number is derived. The subclasses are only in carbon nitrogen ligases. Now in the next slide I would going to request Rikin sir to tell you about typical classes of each one of these enzymes, how they are listed in the Commission, how many entries are there in the EC database. In fact, you need not to remember everything about this database information, because this is just to give you some idea about how the information are organized. We have tried to put a sample before you, that if you refer into the enzyme database structure or EC database structure, this is the way you are going to retrieve the information. So the having a look at the slide is going to give you some idea about the naming pattern which is in practice presently for different classes. So I would request Rikin sir to tell you something about these classes in detail.
So,
Rikin sir.
as Yagnik sir has discussed in greater detail about naming and classification pattern which is given by Enzyme Commission, that what type of exact rules to be followed, and as the example we have taken, that is very famous one, that is EC 1.1.1.1, then what all one means for or stands for, and likewise any type of the number you just think means it is there for some enzyme, then you will be able to understand if you go through the all different legal rules, or you can say the rules and regulations which is given by Enzyme Commission, then you will be able to understand and retrieve the information regarding the exact enzyme and the enzyme as well as the reaction which has been carried out, as well as the substrate on which it will be acted upon. So here we are now trying to list out some different enzymes, the name of the enzymes under the specific classes, as we have discussed and understand now that there are 6 basic classes. So as it is very clearly now known that EC1, we are taking examples of first class, that is oxidoreductases. So EC1 denotes for all oxidoreductases. So subclass, if it is EC11, then it will be acting on the CHOH group of donors. It means CHOH group, if it is acted upon, then the name should be EC1.1. Then 2, it is aldehyde or oxo group, and so on. So different types of examples we have tried to listed upon. I think it is not possible to read out or to explain out all these names here because of the limits of time, but 1, 2 or 3 we will try to discuss you for any for all classes. As we now understand the second class, that is of all transferases, the basic understanding is clear in our mind that in this group whatever the enzymes will be listed will be doing one thing in common, that is they are going to transfer some chemical functional group. So the transfer of functional group is a basic requirement for all the enzymes which are covered or listed under this category. So when you take the example, it will be start with EC2 class, that is transferring one carbon group. If it is the case, then the number should be EC2.1. Then EC2.3, then acetyl transferases will be there. If we want to transfer, or if the enzyme is transferring nitrogenous group, then the number will be EC2.6. Likewise 2.7, 8 and all, they are transferring different type of the functional group like molybdenum and all. So that was all about the transferases class. Now the third class, that is hydrolases, right? So in this class, as we understand that the participation of hydrolysis occurs, right, and all this type of the enzymes will do the hydrolysis, that can be grouped together in this class which is known as EC3 hydrolases. If it is EC3.1, then it will be acting on the ester bonds. Then if it is in EC3.2, then they are glycolysis, and some will acted upon CN bonds and peptide bonds and halide bonds and phosphorus nitrogen bonds. So so on, it will be grouped and named like this, denoted by this EC3 point something, that is 1, 2, 3, depending upon the type of the bond which has been acted upon. So that is about that class. Fourth class, that is the group of enzymes which will go for lyases, that is comes under the class that is known as lyase. The examples we have tried to list it out, that is the EC4.1, that is for carbon-carbon lyases. If the molecule which is acted upon will be making carbon-carbon position, it will have been acted upon by this position, then it is carbon-carbon lyase, that is 4.1 EC. EC 4.2, that is carbon oxygen lysis. If it is EC 4.4, then you can see the things that it is been acted upon by carbon sulfur lysis. Then if it is 4.99, then it is other lysis. So that is the case. Now 5, that is isomer classes, isomerases. As we have discussed also, that in this group the listing of the enzymes will be there, that the enzymes will act upon the substrate and convert that substrate into the product, which will be the isomer of the substrate. So depending upon which type of the isomers are created, which type of the reactions are going on, like on the basis of that, this type of the examples can be denoted. First one, as it is 5.1, that is racemase and epimerases. Then, as sir has discussed this particular example in detail, that is cis trans isomerases, that cis and trans positions can be gained by the action of the enzymes, that can be denoted as EC 5.2. 5.5, that is intramolecular lysis, and if it is EC 5.99, then some other isomerases can be there. So that is the group what we have discussed, that is isomerases. Now last group that what we'll discuss, and we'll try to list out some examples for that. That is the last group is ligases. As we have discussed, that in this particular group, the enzymes which will do the function, that is of joining the bonds, right, between two substrates, that type of the enzymes will be listed upon. If the name the number will be of enzyme commission 6.1, then they will make the bond forming between carbon and oxygen bonds. If it is 6.2, they will give carbon sulfur bonding. If it is 6.3, they will form carbon nitrogen bonding. If it is 6.5, they will give the phosphorus ester bonding. And if it is 6.6, then they will form the nitrogen metal type of the bonds. So these are some various examples of the exact names, that how this type of the naming of enzyme is been done, and after naming it, which type of the classification should be done. So as we all understand that classification and nomenclature both are interrelated, and without the idea of one, another cannot be understood properly. So for that, IUB has done the great work to give us a particular idea by only the number, right? And the name, as we discussed, there are two names for any type of enzyme. One is a trivial or a common name, another is a systematic name. But this idea to give the number denotion for each and every type of the enzyme will work very greatly, that by taking the considering all the aspects what we have learned today, I think from this lecture you will be also having the idea if you will come across to this type of the phenomena or this type of the structure, that if it is EC1111, then what type of the enzyme it is, what should be the structure of that, which type of the substrate will be utilized, and which type of the reaction will be catalyzed by this enzyme on that substrate. So I think this will give you much understanding, better understanding about learning the enzymes and learning the nomenclature and classification of the enzyme. So we are here very thankful to all of you for listening us patiently, and that is all right now from here. Once again, thank you very much, sir.
So dear friends, you have learned a lot about naming and classifying the enzyme in today's discussion, in the discourse given by both of us. Now next time whenever you read in the book about typical enzymatic names, just try to identify by yourself whether it is a trivial name or it is a systemic name, or what EC number could be given to this, or under which EC number this enzyme must have been listed. Another thing I would like to recommend you very strongly is to visit the website of this commission, wherein you are requested to look into the information about any one enzyme, and an elaborate set of guidelines given over there. regarding naming and classifying the enzymes. The rules are so much elaborate that it is really a challenging task to name an enzyme, especially when you have thousands and thousands of enzymes. Every day new information about the new enzymes is pouring in, and the commission need to update its database very often. The list grows by leaps and bounds, and also your predecessors have left behind a lot of confusion. They have used the name of the enzyme in an ambiguous manner. Enzymes have wrongly been named, reactions have wrongly been identified and classified. So amidst correcting all this, you have to reclassify the new enzymes. So